Good morning, guys. Anjani Kumar here, dealing instrumentation subject for a final year electrical students. In the last session, we started about the concept of digital voltmeters, right? So we have discussed about the block diagram representation and what is the difference between analog voltmeter and digital voltmeter. And after that we discussed about a working of a digital voltmeter, some advantages that we discussed. Alright, in today's session we are going to discuss about different types of a digital voltmeters, right? So before going to that new session, I just want to give a brief analysis of what we discussed yesterday, like about digital voltmeters, right? So I just want to give brief analysis, that's it. So before going to new session, it will be very advantageous for new people, those who are watching these videos, right? So first, digital voltmeter, right? So what is a voltmeter? We discussed about what is a voltmeter. So voltmeter is a device which is used to find the potential difference between the 2 points, right? It may be a AC voltage or it may be a DC voltage, right? So we have two different types of voltmeters. Those are analog voltmeter and the other one is a digital voltmeters, right? So in analog voltmeters there will be a pointer which deflected over a calibrated scale, right? When the pointer stops, that's my reading, right? In the case of digital voltmeter, like discrete numerical values, right? It will display discrete numerical values over a LED screen, right? So whatever the observational error, with the help of analog voltmeters, you will get different types of observational errors also. But while reading, there will be a parallax error. It's very difficult to identify an accurate value with the help of analog voltmeters, right? So in the digital voltmeter, we don't have that type of errors also. So that's why we are using nowadays in our laboratories to find whatever the voltage, current, all these things with help of digital voltmeters. Alright, so why? Because the digital voltmeters are more versatile and accurate instrument. So why we are calling a versatile instrument means it's very low cost, right? Low cost, less size, and whatever the power consumption for these type of digital voltmeters is very less and more accurate. So that's why we are calling a versatile instruments. Right. So in the last session we discussed about the block diagram also. The block diagram means how it will be means it consists of one AND gate, it followed by the inverter, and it followed by the counter and 7 segment display. Right. So whatever the input, first it will give to the pulse generator. So this is the input signal. One of the input for AND gate is the output of a pulse generator, and here you will apply a train of pulses. Alright. So this is called a pulse generator. This is AND gate, logic gate. Alright, this is inverter. This is counter. Right, I don't want to explain briefly. In the last session, I explained clear, right? So here the reset pin is there. Alright. So what is the function means whatever the input voltage that you want to find the conversion on analog to digital that can be applied across the pulse generator. Right. So pulse generator is a device which is like a voltage source. It's having a digital circuits and analog circuits, right? So it will convert whatever the input signal that given to that pulse generator, it will convert in a rectangular wave. Right? Let's look at rectangular wave. Alright. So the width and the frequency controlled by a digital circuit in a pulse generator, Right. So whatever the rise time, voltage, rise time, fall time, these are controlled by the analog circuit in a pulse generator. Right. So whatever the output from the pulse generator, that is nothing but a rectangular output which is given to the AND gate. You know about the function of AND gate. If both the inputs are high, the AND gate will show the result. Otherwise, there is no result. Alright. So another input of AND gate, we are applying train of pulses or a clock pulses that you are applied. Right. So whatever the output of AND gate, which is a train of pulses which is related to analogous to the rectangular wave. So when the rectangular wave is high, that high clock pulses will combine, then train of pulses will be generated. See, if this is high and this one is high, then only the output is going to be high. Hope it's clear, right? So if this is high always, right? So whatever the rectangular input is high, so in this portion your rectangular input is high. So what is the rectangular input? How you are getting the rectangular input which is analogous to the input that you applied, right? So both are high, then you will get the train of pulses. Now whatever the output of AND gate, which is a train of pulses which is analogous to the rectangular wave. So when the rectangular wave which is analogous to the input that you applied. So after that, whatever the output coming out from the AND gate which is given to the inverter, so it can invert the clock pulses or a train of pulses, because it will be very easy to understand how many pulses are generated for a counter. Then after that, whatever the output from the inverter, it will be sent to the counter. So the counter will count how many clock pulses. So with that pulses, my digital display will display, LED display is there, it will display whatever the digital signal for the given input signal. So this is the actual black diagram representation of the digital voltmeter that we discussed. Hope it's clear. Nothing is, I just explain how the digital meter will work. Right? Always whatever the analog signal which is converted to digital form, that's it. And after that we discussed about the advantages, right? So what are the advantages? Whatever the generation, digital pulse, digital signal, so that can be stored for a long period also with some techniques. Right? It's a versatile. It can be used roughly. So if you use analog voltmeter, if any fall down from the table, definitely the pointer will get damaged. So it will show errors, right? So, but we don't have that problem with digital voltmeters, right? Analog voltmeter doesn't provide any negative result. So, but the digital voltmeter will provide. Right? It's a less cost, less power consumption, more accurate. Right? So these are the more advantages that we discussed in our last session. I hope it's clear from my side. Right? In today's session, we are going to discuss about different types of digital voltmeters. Right? These concepts are very, very important, right? So each and every voltmeter will take one session, right? So with this you will clearly understand, right? First I'll write what are the different types of digital voltmeters that we are going to discuss. So after that we will discuss one by one, right? DVM is nothing but digital voltmeter. The first one is counter type DVM, right? And second one is successive approximation type. DVM. Next, third one is ramp type DVM, right? And the fourth one is dual slope integrated type DVM. And the fifth one is continuous balance type DVM. Alright, and the sixth one is microprocessor based DVM. Alright, and the second one is a digital frequency meter. Right, frequency, how we can find out the frequency in the form of digital nature, right? And the eighth one is phase angle meter. Phase angle also we can display in the form of digital form. Phase angle meter. Right. So these are the whole content of this unit. Regarding this unit consists of whole different types of digital voltmeter. That's it. So if you strictly follow these videos, that what I am taking all the digital voltmeters, and definitely will get good information, no doubt about that, right? So it consists of a block diagram representation. We'll discuss further, right? So there are basically 8 types of digital voltmeters. That is a counter type DVM, successive approximation type DVM, ramp type DVM, dual slope integrated type DVM, and continuous balance type DVM, microprocessor type, digital frequency meter, digital phase angle meter. Right. So in this we will discuss all the things with neat examples also. But very most important concepts are, the first one is successive approximation, which is very important. After that, somewhat ramp type, and it's very important, like a dual slope integrated type. Remaining all, this is somewhat important. Remaining all, definitely maybe we will get the question, right? Right. So these are the different types, and these are most important concepts, right? So you have to stress on that more, right? That's what I said. We'll discuss each and every DVM in detail, no doubt about that. Right. Right. The first DVM we are going to discuss this session is counter type DVM. So each and every DVM for one session, right? I'll take one session for this. So with that I'll clearly explain, right? Right. These type of DVMs, I don't want to write anything. I just want to draw the block diagram first for every DVM. Right? So after that I'll explain each and every block. Right? So after that I'll explain the functioning, working. Alright. So after that, with an example, we will conclude with an example. Right. So I'll take one example. So how the analog data which is converted to digital form. So with that I'll conclude the DVM. Alright. Next. So what is a counter type DVM? So I'll write the block diagram first. See the block diagram. You have a comparator. So whatever the one input of AND gate from the comparator, and this is clock pulses. Right. This we can call it as an AND gate. So there is nothing but logic gate. AND gate or a logic gate. Right. So this is called n-bit counter. right? So this is a binary display, right? So this is a digital to analog counter, right? So this is a comparator, so which whatever the input that you applied here, this is a comparator, right? So this is a whatever the output of a counter, so that we can call it as a D. So digital is converted to analog, na? So that is called counter. So this is a plus and this is a minus, right? So now I'll explain. So this is a block diagram representation of a counter type DVM. So why we are calling a counter type means, which is nothing but which we are using a counter, n-bit counter. So that's why we can call it as a counter type DVM, right? So here the first block is a n-bit counter. So it's a counter which counts how many clock pulses, right? Which counts how many clock pulses from the logic gate. That's it. That function of this thing is that. So how many clock pulses from the logic gate? If there is 2 clock pulses, it will show LCD display 2. If there is 1 clock pulses, it will take 1, right? Again, whatever the output of n-bit display, n-bit counter, which is given to the digital to analog converter, right? Digital to analog counter, so, right? So whatever the data that coming out from the counter, digital data which is converted to analog. So why we are using analog means we will see, right? After that, whatever the output of digital to analog counter, which converter, which is given to the comparator, right? It's a comparator means the comparator requires analog data only, right? That's why we are converting whatever the digital data from the counter which is converted to analog form, because whatever the counter, it requires only, it accepts only analog signals, right? And one input which is given to the, which is given the whatever the unknown voltage. If you want to convert what the unknown voltage which is converted to digital form, that you can apply here, right? So when comparator will work means, whenever whatever the input which is greater than the VD, so then only it will send a signal, set signal. See, first you should know the operation of AND gate. When AND gate operates, both the inputs are high, right? So always your clock pulse is at high end, right? So whatever the output of a comparator, when it will high means whenever the positive signal which is greater than the negative signal, so then only the comparator will work, it will give high. So when the both are high, then definitely AND gate will operate, right? So when this comparator will work means, when Vin greater than VD, so this comparator will generate the set signal, okay? That is a 1, right? If both are high, definitely there will be output of AND gate. So then the counter will count, then digital to analog converter, whatever the output, again it will be fed to the comparator. The comparator will check whether the input is high or no. If it is low, definitely it will false 0. If there is no 0, there is no counter, there is no output from the AND gate, there is no counter. Hope it's clear, right? This is the working of a counter type DVM. So nothing is there. It is having a 4 blocks. First block is n-bit counter, which will count the number of clock pulses, and digital to analog counter, it will convert whatever the digital form into analog form that can be applied to the comparator, right? So one end of the comparator which will go the input which we are converted to digital form. So after that, these two are going to be compared. So when this comparator satisfy the set signal, if it is a reset, there is no operation of AND gate. AND gate when operates, both inputs are high, the AND gate output is high, then only the AND gate will work. If one input is high, output is 0. If one input is 0, output is high, 0. So both inputs should high. When the comparator will give a set signal, when Vin greater than VD, the comparator will set the signal. So both the inputs are high, generate the clock pulses, counter will count the clock pulses. That's it. Now I am taking the example. See, now my input is right? So what I am giving my input is a 3. So this we can convert it to analog form. We'll see. First, initially n-bit counter will work from 0. There is no output, so there is no output from the AND gate. So right, so initially n-bit counter will show 0 value, 0 clock. Is there any clock pulses from here? There is no clock pulses. So what is the value? Value must be 0. Alright, so then whatever the data which is converted to digital to analog converter, so what is the value? Value here is a 0. Alright, so that means V in greater than VD. Is it right? So 3 greater than 0. Okay, so the comparator will work, right? It will set the AND gate, so generate the clock pulses. All AND gate one input is always high. The other input is also high. The AND gate will perform. It will send one clock pulse. Right? It will send one clock pulses. Okay. Then n-bit counter will count how many clock pulses. One clock pulses is there. Right? One clock pulses is there. Then it will give the display 0, 0, 1. So then digital to analog converter. So it will treat it as 1. Again 3 is greater than 1. Is it right? Yes, 3 greater than 1. Again it will set 1. Both are high. It will generate another clock pulse. Right? So then counter will count how many clock pulses. There are 2 clock pulses. So 0, 1, 0. So what is the value of digital to analog converter? It is a 2. So again compare whatever the input 3 greater than 2. Yes, is it right? Again it will set the signal. Right? Both inputs are high and it will perform the operation. Again it will generate the clock pulse. So how many clock pulses? 3 clock pulses. Click pulse. So what is the value? 0, 1, 1. So what is the value? 3. 3 greater than 3? Not. So how the comparator will show 0 value. When one input is 0, AND gate will block. There is no output from the AND gate. Then n-bit counter will set how many clock pulses? 3 clock pulses. Then this 3 will give the result. So what is the given? What is my input? Analog data. Analog input is 3. What is my output? 0, 1, 1. Right? So my analog data which is converted to digital form. So like this the counter will work. I hope it's clear. Nothing is that. Simple. Whatever the voltage that you want to convert analog to digital form, that can be applied across the comparator. Right? Initially n-bit counter will count how many clock pulses. Initially is there any clock pulses from the AND gate? There is no. It says 0. Again it will be converted digital to analog. So 0 is nothing but 0. So then it is given to the comparator. So the comparator will check whether V in greater than VD or not. Yes, definitely 3 greater than 0. Is it right? So the definitely set signal will send to the AND gate. AND gate one input is clock pulses. Always clock pulses are high. Both inputs are high. Definitely AND gate will work and generate the clock pulse. Okay, first clock pulses moves to the counter. The counter will count how many clock pulses? 1 clock pulses. Then again 1 will be shown. Again this one converted to digital to analog converter. 1 will enter into the comparator input. 3 and 1 will check. 3 greater than 1. Yes, it's true. Again set signal. Again generate clock pulse. So how many clock pulses there are? There are 2 clock pulses. And then again 2 will be 3 greater than 2. Okay, set signal will be there. Again clock pulses. How many clock pulses here? Now 3 clock pulses is there. 3 clock pulses. Whatever the digital analog converter, the final value is 3. 3 greater than 3. Is it true? No, it's a false. Then comparator will show reset the AND gate pin. If it is resetted means both one input is high, another output is 0. And AND gate, is there any clock pulses from the AND gate? There is no operation of AND gate. Then counter will decide the 3 clock pulses. The counter will display the digital signal, gives that is analog to digital form. Hope it's clear. in this way the counter type will go. So the main drawback of a counter type means if it is 3 starts from 0, 1, 2, 3. If it is 6, right, it starts from 0, 1, 2, 3, 4, 5, 6. So like that, how many clock pulses that you require for for digital to analog converter? If it is n bit, how many clock pulses you require? 2 power n minus 1 clock pulses you require. Alright, so that means 7 clock pulses you require. If it is a 6, right, how many? If it is n bit 3 means there are 0, 1, 2, 3, 4, 5, 6. So if you take this number of clock pulses is much, 7 clock pulses you require. So each and every time you are generating a clock pulses, it should be very difficult. So that's why this is a time consuming process. If you want to find out all the 3 things that you are going to, 3 clock pulses that you have played, the result will be shown after ending of the clock pulses. If it is a 4, definitely it will start from 0, 1, 2, 3, 4, then will display. If it is a 6, starts from 0, 1, 2, 3, 4, 5, 6, and then it will display. Like that, it's a time consuming process. So number of clock pulses required is very high. So in order to avoid these time consuming process, so we developed another digital voltmeter that is called successive approximation digital voltmeter. Right, so this is about the counter type digital voltmeter. So what is the main drawback of this counter type digital voltmeter is number of clock pulses is 2 power n minus 1. That hope it's clear, right? How many clock pulses required? If it is a 3 bit, 7 clock pulses is required to find out 7, 6, 4, 5, 4, 3, 2, 1, 0. So each and every time, if you want to find out the 2, starts from 0, 1, 2. Right? If starts from 3, starts from 0, 1, 2, 3. Right? Number of clock pulses are required. 2 power n minus 1 clock pulses are required. So this is the main drawback. So how many components that we have in a counter type digital voltmeter? There are n bit counter, digital to analog converter and comparator and logic gate. So why the comparator? Why the digital to analog? That means whatever the comparator that require only analog input, that doesn't accept the digital value. That's why we have a digital to analog converter. These two will be there. When the comparator will work means whatever the V input greater than VD, then only it will set. Otherwise reset. If it is once it is reset, there is no output from the AND gate. Hope it's clear, right? So this is the working of a counter type DVM, right? So in the next session, thank you for now. In the next session, we will discuss about the successive approximation type digital voltmeter. Right, it's very important thing. So in order to overcome the drawbacks from the counter type digital voltmeter, we implemented the concept of successive approximation type digital voltmeter. Right, we'll discuss in the next session. Thank you for now.